In this example of American Heart Association donations, I will show you how to set up the simulation problem and simulate it using at-risk. As you read the question, please think about the randomness or uncertainties involved in here. Now, pause the video and read the question. Okay, I can think of 3 sources of uncertainties here. 1. When someone answers the door, will it be a man or woman? 2. Will the person make a donation? 3. How much is the donation? We try to estimate the average amount of donation by accounting for these different sources of uncertainties that are prevalent in a lot of real-life business simulations. Let's take a look at the several elements in this business simulation problem. The output is the average donation. The 3 sources of uncertainties that we just described, namely the gender of the person who answers the door, whether this person makes a donation, and the amount of donation are all probabilistic inputs. Other inputs that can be controlled include the time of visits, the number of visits that can be determined by the association. Once we have all the inputs ready, we can calculate the amount of contribution from one household, and the average contribution from many households can be easily calculated as well. These 4 elements are very helpful for us to set up the simulation model, especially identifying the inputs, outputs, and the relationship among them. We're going to use at-risk functions to simulate the probabilistic inputs. Let's take a look at the first question. If someone answers the door, will it be a man or woman? Here, we are simulating the gender of the person. The past experience shows that the person who answers the door is a woman 80% of the time, and a man 20% of the time. If you're going to use 0 to represent a male, and a 1 to represent a female, we would like to generate a random number that is 0 20% of the time, and 1 80% of the time. The at-risk function risk-discrete can do this job. Risk-discrete takes 2 arguments. The first argument includes all the outcomes, which will be 0 and 1 for our case. The second argument includes the corresponding probabilities for each of the outcomes. For 0 or male, the probability is 20.2. For 1 female, the probability is 0.8. You could also place 1 in front of 0. Just be sure to swap the corresponding probabilities as well. Also, be sure to use curly brackets to follow the syntax for risk-discrete. For the second question, will the person make a donation? Well, this depends on the gender of the person, which was just generated in the first question. Women would make a donation 70% of the time, and a man would make a donation 40% of the time. We are going to use 1 to represent a donation is made and 0 to represent no donation. Due to the different donation behavior of men and women, we need 1 variable for each gender. The variable for women would be 1 or yes with 70% probability and a 0 or no with 30% of the probability. The second variable for men would be 1 with 0.4 probability and 0 with 0.6 probability. These 2 variables can be generated using risk-discrete. They are risk-discrete 0.1, 0.3, 0.7, and risk-discrete 0.1, 0.6, 0.4. The third input is the amount of donation. Well, this is different from the first 2 variables in the sense that it is no longer a binary variable that is either 0 or 1. Instead, this variable is the actual amount being donated, so a numerical variable. This variable again is different for women versus men, as the contribution from females is normal with mean 20 and a standard deviation of 3. And that of male is $10 as the mean and $2 as the standard deviation. So we would need to generate 2 variables again. This can be done using risk normal. The first argument is the average of the normal distribution, while the second argument is the standard deviation. Let's set up the model using at-risk functions. First of all, explicitly type out the 3 types of probabilistic inputs. I did that in column A, as you can see here. Column B is where the variables are generated. To show you the exact formulas I typed in column B, I also typed them out in column C. When you create this spreadsheet in Excel, you will not need to column C, as these are the formulas you should enter in column B instead. Let's consider one particular visit. A female answered the door because the value is 1 in cell B1. She made a contribution because the value 1 in cell B3, and the total contribution is $20 in cell B4. Therefore, the total contribution in cell B10 is also $20. This is indeed what was calculated using the if function in B10. If B1 is 1, that's our case here, we return B3 multiplied by B4. Consider another visit. Again, a female answered the door, but she did not make any contribution because the value is 0 here. Therefore, the total contribution in cell B10 is always 0, regardless of the number in B4. This number is also what's being calculated using the if function. If B1 is 1, that's our case here, we return B3 multiplied by B4. Consider a third visit. A male answered the door and made a contribution of $12.42. The total contribution from this visit is $12.42, which can also be calculated using if function. In this if function, the condition is not met. That's because it was a male, not a female, who answered the door. And the returned value will be the third argument of the if function. That is B7 multiplied by B8. That's exactly $12.42. Simulate this problem using at-risk. The first step involves setting up the variables. I've already done that using a risk discrete variable here, risk normal here. The second step involving pointing out what the output variable is. That's going to be the contribution from each household. That's B10, as you can see here. I click on B10 and I click on output. And sometimes you may see define, you click on define, but over here, I'm just going to click OK. The third step involving setting the number of iterations. That means how many scenarios you would like to simulate. And I'm putting 2,000 here. You can use some other reasonably large number, but I would highly recommend you to start with a smaller number for your first time because you probably do not want to crash your computer in the first time. The fourth step is to click on simulate just to start the simulation. As you can see, at-risk started doing that. And if you don't see the same graph as I do, what you can do is you can move on to step 5 and click on explore, distribution, automatic. And so this is the same graph we see here on the left, and there's some summary statistics on the right. Okay, so from the summary statistics, we know that out of 2,000 iterations, the average donation is about $12, and the standard deviation is about 9.79 or $10 here. Okay, and the median donation is about $16.6. And this graph on the left is actually super helpful. For example, by changing this, we're able to tell what is the percentage to the left. For example, if the association is true, to analyze what is the percentage that they will not be able to receive any donation, you can change this number to 0. And that means on average, it's about 35% of the time, the association will not receive any contribution for each visit. And if I change this, say, to $20, and the percentage shown on the right indicates that about 29% of the time, the contribution is going to be more than $20. You can also change the number here. For example, I'm going to change it to 95%. 95%. That means the 95% confidence interval we have for this particular business simulation problem, the donation is anywhere between $0 to $25, right? $25. So this is super powerful. And you can also click on this sensitivity view. For example, go to tornado regression coefficients. What we see here is there are several variables we use to set up this business model. She makes contribution, which is cell B3. Okay, this one has a longer bar here. This actually represents among all the factors here, this particular factor is the most important one. It's the most critical one in determining the contribution for each visit. So if she makes a contribution, yes versus no, this is going to highly detrimental, important for the contribution. And followed by gender of the person who answered the door, a female versus male. So if it's a female, then it's more likely for us to have a higher contribution as well, receive a higher donation, and followed by the amount she contribute. So this is another very useful feature provided by at-risk. In this video, we learned how to use at-risk discrete and risk normal functions to build a simulation model that imitates volunteers going through a community for donations. The simulation results provide an insight into the amount of contribution that the association can expect to allow for a better allocation of volunteer hours.